Good morning all. I am Dr. Sadanand Kumar, Assistant Professor, Department of Physics, AJ Institute of Engineering and Technology, Mangaluru. Today I am going to talk about quantum mechanics. In this session, I will discuss about the following topics: Heisenberg uncertainty principle, application of uncertainty principle, some problems related to the Heisenberg uncertainty principle, wave functions and its physical significance, concept of normalization, and properties of wave function. In classical mechanics, any particle occupies a definite place in space and possesses a definite momentum. So, knowing the particle's position and momentum at any given instant of time, it is possible to evaluate its position and momentum at any later point of time, and the trajectory of the particles can also be continuously traced. So this is the situation in classical ideas or the classical mechanics. But when it comes to atomic scales, where the particle size is of the order of few Armstrongs, in other words 10 power minus 10 meters, the classical mechanics fails to evaluate the simultaneous value of position and momentum of that particular microparticle. So new mechanics called quantum mechanics takes over, in which one of the fundamental principle is Heisenberg uncertainty principle. Measurement of physical parameters becomes quite difficult in a quantum particle. However, in case of a quantum particle, there are uncertainties associated with the position and momentum of wave packet, which represent the particle. Let us consider a wave group which is formed due to superimposition of two or more waves traveling with slightly different wavelengths. A wave group is shown in the slide. A particle corresponding to this wave group may be located anywhere within the group at a given time. If the wave group is narrow, the more precisely particle's position can be measured. But the wavelength of the waves in a narrow wave group, it is not well defined. Since lambda is equal to h by p, is from the de Broglie hypothesis, the particle's momentum is not a precise quantity, which means if the wave packet is narrow, we can determine the position of the particles accurately, whereas wavelength of the particle is not defined. It's quite difficult to evaluate the momentum value there. On the other hand, a wide has a clearly defined wavelength, therefore momentum corresponding to it is a precise quantity, but the width of the group is too large to say where exactly the particle is at a given point of time. So which means the wavelength of the wide wave group can be easily evaluated, whereas the position of the particle can be quite difficult if you want to go for the simultaneous measurement of these two parameters. Thus, the introduction of the uncertainty principle given by the Heisenberg. Statement of the Heisenberg uncertainty principle: in any simultaneous determination of position and momentum of a particle, the product of the corresponding uncertainties inherently present in the measurement is greater than or equal to h by 4 pi. where h is constant. H by 4 pi is such a small fraction it is. Mathematically we can write delta x into delta p is greater than or equal to h by 4 pi, where delta x is the uncertainty in the measurement of position and delta p is the uncertainty in the measurement of momentum. This Heisenberg uncertainty principle is also applicable in the another pair of physical parameters, namely in the measurement of energy and time of a particle. So, statement of Heisenberg uncertainty principle for energy, time, physical parameters. It states that in a simultaneous measurement of energy and time in a physical process, the product of the corresponding uncertainties inherently present in the measurement, which is greater than or is equal to h by 4 pi. Mathematically we can write delta E into delta T is greater than or equal to h by 4 pi, where delta E is the uncertainty in the measurement of energy and delta T is the uncertainty in the measurement of time. Heisenberg uncertainty principle is also applicable to angular displacement and angular momentum. So, statement of this is, in a simultaneous determination of angular momentum and angular displacement in a physical process, the product of the corresponding uncertainty is inherently present in the measurement and is greater than or equal to h by 4 pi delta L dot, that means delta L into delta theta is greater than or equal to h by 4 pi, where delta L is the uncertainty in the measurement of angular momentum and delta theta is the uncertainty in the measurement of angular displacement. Now we have seen Heisenberg uncertainty principle for the various pair of physical observables. Now it enables us that one should not think of the exact position or the accurate value for the momentum of a particle. Instead, one should think of probability of finding the particle at a certain position or of the most probable value for the momentum of the particle. So which means instead of going for the accurate value of the position and momentum when we go for the simultaneous measurement, it is quite a bit difficult. So instead of that, you can go for the probable value of the position as well as the probable value of momentum when we think of a simultaneous measurement. That is what the physical significance of the Heisenberg uncertainty principle. And similar interpretations can be made for the canonical conjugate pair, that is delta E and delta T, also delta L and delta T. Of course, we know what is delta L and delta theta. Delta L is the uncertainty in the measurement of angular momentum. Delta theta is the uncertainty in the measurement of angular displacement. Now, let us see the application of Heisenberg uncertainty principle. To discuss the application, let us take the topic that non-existence of electron inside the nucleus. Non-existence of electron inside the nucleus, this concept is similar to similar or related to the beta ray emission, that we have studied in our basic nuclear physics. It is known that during the radioactive decay, three kinds of rays, namely alpha ray, beta ray and gamma radiation, emitted from the radioactive nuclei. In 1900, scientist named Henry Becquerel demonstrated that beta rays are stream of electrons and they emitted electrons, they having a different velocities. The corresponding kinetic energy of the emitted electrons is of the order of 3 to 4 mega electron volt. Now the prime question is it possible that electron exists inside the nucleus with the certain energy, and the same energy appears as their kinetic energy when they are emitted? This can be argued on the basis of Heisenberg uncertainty principle. For this discussion, let us consider an atomic nucleus. Its diameter is approximately 10 power minus 14 meters. We can take this value is approximately the maximum space confinement for an electron. Thus, if electron exists inside the nucleus, then the uncertainty in its position is that must not exceed the value of 10 power minus 14 meters. Therefore, uncertainty in the measurement of position of an electron is 10 power minus 14 meters. Delta x is the value 10 power minus 14 meters. In turn, one can evaluate the uncertainty in the momentum using Heisenberg uncertainty principle. That we can see in the slide. Delta P is greater than or equal to 0.5. In fact, 0.527 into 10 power minus 20 kg meter per second. This is the uncertainty in the measurement of momentum of the electron. Then the momentum of the electron must at least be equal to the uncertainty in the momentum, which means whatever the uncertainty in the momentum value we got, that can be treated as the momentum of the electron. Therefore, the momentum P is equal to 0.527 into 10 power minus 20 kg meter per second. The energy of the body is given by E equal to P square by 2m. That's again the relation between kinetic energy, the momentum. So E equal to P square by 2m. In order that the electron may exist inside the nucleus, its energy must be such that E should be greater than or equal to P square by 2m. Now if you substitute the value of mass of the electron, that is 9.1 into 10 power minus 31 kgs, and momentum value which we have taken from the previous discussion, that is 0.527 into 10 power minus 20. So this will lead to the energy as 1.372 into 10 power minus 11 joules. You convert this energy into electron volt, it is approximately greater than or equal to 85 mega electron volt. 85 mega electron volt. Okay. Now if the electron exists inside the nucleus, its kinetic energy must be greater than or equal to 85 mega electron volt. But experiments show that the electrons emitted from the nuclei, the energy of these electrons is about 3 to 4 mega electron volt. Therefore, there is a mismatch in the experimental and theoretical value of energies. From this, we can conclude that the electron is not existing inside the nucleus. Electron cannot exist inside the nucleus. So let us see some problems related to the Heisenberg uncertainty principle. The first numerical, the position and momentum of an electron with energy 1 kilo electron volt are determined. If the inherent uncertainty in the measurement of its position is 1 angstrom, what is the minimum percentage uncertainty in its momentum? In this problem, we are supposed to determine the percentage uncertainty in its momentum. The given parameters are, first thing, the energy, the kinetic energy of the electron is given, that is E is equal to 1 kilo electron volt. To convert kilo to kilo as 10 power 3 and electron volt into joule, that is 1.6 into 10 power minus 19, that much joules. 1 into 10 power minus 3 into 1.6 into 10 power minus 19 joules, it will be reduced as 1.6 into 10 power 16 joules. And also the other parameter is given, the uncertainty in the measurement of position is 1 Armstrong, which means delta x is 10 power minus 10 meter. 1 Armstrong value is substituted. Then using the uncertainty principle, delta x into delta p is greater than or is equal to h by 4/5. We can evaluate delta p. But the unknown parameter is the percentage uncertainty. In order to evaluate the percentage uncertainty in momentum, so we need to have a value of the momentum too. So you have the relation between the kinetic energy and momentum, that is P equal to square root of 2me, and energy value is already we have substituted the electron volt as well as the conversion of kilo into 1000. That value we have just substitute energy term in the equation. We'll get momentum as 1.7 into 10 power minus 23 kg meter per second. And the percentage uncertainty in the momentum is uncertainty in the momentum by momentum into 100. So if you substitute this calculated values of uncertainty in momentum and momentum in the equation and multiply that ratio into 100, it gives rise to 3.1. That is the answer for the problem. We'll go to the second problem. In a measurement of position and momentum that involved an uncertainty of 0.003%, the speed of an electron was found to be 800 meter per second. Calculate the corresponding uncertainty that arises in determining its position. Here the given parameters are velocity, that means speed of the particle is given. Second, uncertainty involved in the measurement of the velocity is given, that is 0.003%. Uncertainty involved in the measurement of position, delta x, is unknown. Now first you convert delta v, because percentage is given, you have to convert into a fraction. So let us write delta v, that means inherent uncertainty in the speed is delta v is equal to 800 into 0.03%. That means that fraction divided by 100, that will give rise to the uncertainty in the measurement of speed. So it will be roughly 0.024 meter per second. Uncertainty in the measurement of momentum we can calculate. Here the uncertainty in the momentum is not given directly, but you can evaluate because we have the delta v value there. So delta p equal to m delta v, because we know p equal to mv, that concept, can write delta p equal to m into delta v. So it will be 2.184 into 10 power minus 32 kg meter per second. And uncertainty in the measurement of position is now easy to calculate using Heisenbergs uncertainty principle. We substitute these data and it will be greater than or equal to 2.4 into 10 power minus 3 meters. That is the answer. Third numerical, the inherent uncertainty in the measurement of time spent by iridium-191 nuclei in the excited state is found to be 1.4 into 10 power minus 10 seconds. Estimate the uncertainty that results in its energy in the excited state. So in this problem, the given parameters are the delta t, that means uncertainty in the measurement of time. So time in which the electron that can stated in the excited state is given, it's 10 power minus 10, of course 1.4 into 10 power minus 4 minus 10 seconds, and delta E, uncertainty in the measurement of the energy, meanwhile it's unknown parameters. So we have a expression for Heisenbergs uncertainty principle in terms of energy and the time, direct substitution. So delta E is 3.77 into 10 power minus 25 joules. Convert joule to electron volt by substituting electron volt value, that is 1.6 into 10 power minus 19. That will be equal to 2.35 into 10 power minus 6 electron volt. Therefore, minimum uncertainty in the energy of the nuclei in the excited state is 2.35 into 10 power minus 6 electron volt. Next concept is wave function. According to the postulates of quantum mechanics, there exists a function determined by the physical situation. Such a function is called wave functions. So it is clear from the quantum mechanics that any physical observables which are present, correspondingly there is a function. So corresponding functions are called wave functions of that particular physical observable. It is denoted by a symbol psi, psi. In other words, the quantity whose variation make up matter waves is called wave function. Normally these wave functions are designated by symbol psi. The wave functions accounts for the wave-like properties of the particle and contain all possible information about the state of the system. Wave function may vary with respect to both the position and coordinate of a physical system and time. Such a wave is called a total wave function, which means if a wave function varies with both position coordinate as well as the time coordinate, then such a function corresponding to that particular observable is called a total wave function. Total wave function. Representation of the total wave function is capital psi is equal to a into e power I into kx minus omega t. Some of the physical significance of the wave function. In matter waves, the quantity that varies periodically is called the wave function. The second point is the wave function psi is a complex quantity. That means it includes both real and imaginary parts. Hence, wave function by itself cannot be an observable quantity. Third point, even though the wave function by itself has no physical meaning, the probability density, that is modulus of psi square is equal to psi star, is a real and a positive quantity and is a measurable. Probability density is introduced just to get real and positive quantity. So normally the wave function as itself has no physical meaning. To get the physical meaning, what we need to do is you have to multiply the complex conjugate of that particular wave function. That means if psi is the wave function, complex conjugate of the wave function is psi star, then psi star is equal to modulus of psi square. That is nothing but the probability density. So probability density modulus of psi square is the probability of finding the particle in a unit volume, and it can have values anywhere between 0 to 1. 0 means the chance of finding the particle is 0%, and 1 in the sense the chance of finding the particle is 100% at a given point of time in the space. Intermediate probability, say for example the probability is 0.3, which means there is a 30% chance of finding the particle. Similarly, if the probability density is -2, it has no meaning, it's simply a meaningless. So probability density is never be a negative entity, but the amplitude of the wave can be a positive or negative. Higher the values of the probability density means the probability of finding the particle within a given volume is more. That means higher the probability means the chance of finding the particle in a given region is more. That is what the meaning. The probability 1 corresponds to the certainty of finding the particle, whereas the probability 0 corresponds to the uncertainty of finding the particle. That means not finding the particle in the given region of space. Mathematically, you can write triple integral psi star dv is equal to 1 if the particle is present. The meaning of the triple integral is that represents the three coordinates, x, y, z coordinates, and psi star is the probability density in a given region of space, dv is the volume, that is written as dx, dy, dz. The second equation, triple integral psi star dv is equal to 0 if the particle is absent. Next concept is normalization. So if psi is the wave function associated with a particle, then we have modulus of psi square d tau as the probability of finding the particle in a volume d tau. So we can see the picture in the slide. So imaginary volume tau in which elementally volume d tau is given. Now the probability of finding the particle in a elemental volume d tau is modulus of psi square d tau. So this volume tau is made up of such a large number of d tau elemental volumes. Therefore, the chance of finding or probability of finding the particle in a volume d tau is integrate between 0 to tau modulus of psi square d tau is equal to unity, which means you are highly certain that particle is present in the volume within the volume tau. However, in this case, if you are not able to find the particle within the given volume, in other words, you are not at all certain about the locating the particle in a finite volume anywhere in space, then the expectation extends that it exists somewhere in the space. Then the limit extends, instead of 0 to tau, it should be minus infinity to plus infinity, because we are talking about the particle somewhere in the space, not in the region of space like volume what we have considered tau. Now we are extending the limits from minus infinity to plus infinity, somewhere it is present. You are highly certain that particle is present in the space. Then the probability of finding the particle in the volume dv is modulus of psi square dv. Since the particle is present somewhere in the particular region, the integral of modulus of psi square dv over all the space must be infinite. In fact, it must be finite. If this particle is certainly to be found in the certain region of space, then you can see the expression minus infinity to plus infinity modulus of psi square dv is equal to unity. Yes. Now the function is said to be normalized wave function. So if you say integral between minus infinity to infinity or 0 to tau modulus of psi square dv is or d tau is equal to unity, that equation we can say normalized equation. In other words, wave function is normalized. Very often wave function is not a normalized wave function. That means result of modulus of psi square dv is not equal to unity, but it involves a constant that exists in the equation for psi. However, the actual result obtained is equated to the unity and the values of the constant is determined. It is then substituted in the equation for psi. This process is called normalization. Next next point of discussion is the properties of wave function. The first point is wave function is single valued everywhere. That means there should be a single value or a one probability for the particle to be in a specific location at a point of time. So to discuss this particular point or the property, let us consider one function shown in the slide, the first figure. A wave function shown in the slide, that's first figure, it is not a single valued over a certain intervals in fact. In this example, f of x has three values, f1, f2 and f3 for the same value of p. At x equal to p, and f1 is not equal to f2 is not equal to f3. It means that f of x has probabilities of finding the particle as 3 different values at the same point. Such a wave function is not acceptable. So in order to accept it, it should have a single value at a single point, single value at single points. Okay. Next, the second point is wave function must be finite everywhere. So let us take the example as a second graph in the slide. In this figure, the function is not finite at x equal to r. Second figure, in fact. At x equal to r, f of x equal to infinity. Why? Because if f of x is to be a wave function, it signifies a large probability of the particle at a single location. But that condition is violated here. Hence, the wave function is unacceptable. It should not be any discontinuity in the function. Otherwise, it is not acceptable. And the third point, the wave function and its first derivatives with respect to its variables must be continuous and single valued everywhere. Let us take one more graph to explain this. So in the slide, a function f of x which is discontinuous at q, you can see in the third picture, f of x is truncated at point A and restarts at point B. Between A and B, it is not defined. So if f of x is to be a wave function, then the state of the system at x equal to q cannot be ascertained. That means it is not defined in between that region. Hence, wave function is not acceptable. It should be continuous. There should not be any discontinuity in the function. Otherwise, it is not acceptable. That's why this type of wave functions are not accepting. And the last point is, for a bound state, wave must be, that means wave function must be vanish at infinity. If wave function is a complex function, then psi star must vanish at infinity. Today's class I will stop here, and tomorrow's session I will discuss about the eigenfunction, eigenvalue, and Schrodinger wave equation and solutions to the Schrodinger wave equations. Thank you.